Hello everyone, it's my honor to share our work here. I'm Pengsheng Wang, a student from Shanghai Jiao University. Today, the topic of our presentation is about the problem of 3D hand pose estimation. In our paper, we proposed a new network to handle this problem. Our presentation is divided into 5 parts. Firstly, I would like to introduce the background of our work. As we all know, gesture recognition is widely used in our nature society. For example, it can be used in a smart car for the entertainment system controlling, and it can also be used in VR or AR to improve the customer experience. Although recently, with the development of the computer vision, the gesture recognition has been greatly improved, but it is still a challenging problem because of the large variance, high flexibility, and severe self-occlusion of the hands. The most popular way of hand pose estimation is to estimate the hand joints model from images. We also follow this way. As you can see on the slide, the joints model of the hand is a graph-like data. Many previous works have proved that the structural information of the hand is helpful to the joint's position regression. So many methods have been proposed in recent years. For example, Deep Prior, a work in 2015, proposed adding a prior layer in the neural network directly. Also, they calculate the prior layer through the PCA method before the network trained. In the work deep model, they directly add the handcraft constraints in the neural network training. And in HBE, one work of ECCV 2018, they proposed to use branch network to regress the joint's position. Different branches of the network regress different parts of the hand, and then they contact the features to regress the hand joints model. The traditional convolution network has been proved successful in processing structured data, but for the unstructured data it can do nothing. To overcome its limitations, recently the researchers have proposed a graph convolution neural network to process the graph-like data. They have achieved state-of-the-art performance in many areas, such as multi-label image recognition, video recognition, and human pose estimation. As you can see on the slide, the definition of the graph convolution network is this equation. The y is the output of the layer, and x is the input. W is the width matrix, and A is the adjacency matrix. In this paper, we use a learnable adjacency matrix to exploit the structure information of the hand. By this way, the algorithm can have a better performance. This is the overall architecture of our GHand network. The inputs of our network is preprocessed images, and through a lightweight backbone network, we got initial 3D joins and 256 vectors. Next, we fit this initial joins and the vector to a two-layer graph convolution. And finally, we got the 3D joins. We have two loss functions. First is the initial 3D loss, and second is the final 3D loss. We set alpha is 0.5 to balance the initial 3D error and the final 3D error. And we implement our experiment on the open dataset, on the GHand dataset. It is captured by Microsoft Kinect depth camera. And the dataset contains 72 kilo training and 8 kilo testing images. For the training set, it is collected from one subject, and the testing set is collected from two subjects. We train our network on a single NVIDIA GPU. Batch size is 64, and we train about 200 epochs, and it takes about 8 hours. This is the result of our experiment. As you can see, our JSON layers can significantly improve the performance of the network. And this is a comparison of our network and other state-of-the-art methods. According to these results, we found that the accuracy of the tips joins is highly improved by the graph convolution layer. We think this is because the gesture is well structured by the graph convolution layer, so the tips have a few freedom, so it can be well regressed. And from the results, our method performs better than most other state-of-the-art methods. This is the result shown in the image. Our method have a better performance in the value testing dataset. As you can see in the image, our gesture is well structured. This will be very helpful for the gesture classification. This is a real-time demo of our method. As you can see, this demo is running on a personal computer. Our method is efficient, and it can be run on a simple computer and have a good speed. As you can see on the demo, our predicted gesture is well structured. In the prediction, the gesture didn't deform significantly. This point is very important to the gesture recognition. From this demo, we can see our method is not only accurate but also efficient. Finally, I make a short summary of this presentation. Our main contributions is we propose to use a learnable, adaptive, adjacent matrix to learn the structure infra of the hands. And we also design a novel graph convolution to estimate the 3D hand pose from single depth images. And our experiments showed our method is not only accurate but also efficient in hand pose estimation. In the future, we want to explore and exploit the graph convolution network to enhance the stability and the feasibility of the regression in hand pose estimations. And we also want to study more suitable structure to handle hand pose estimations in different scenarios, such as in RGB images only. That's all for my presentations. Thank you for listening.